Hi everyone, welcome to the part 2 of the flipped classroom lecture on ophthalmic preparations. Part 2 and part 3 of the video will focus on the formulation, consideration and assessment of ophthalmic product. Before we start, there are several aspects which we need to consider for formulating an ophthalmic product. These include sterility, tonicity, pH and buffering, preservation, efficacy, solubility, stability, viscosity, clarity and the presence of allergen and particulates. Let's look at the first factor, clarity. We must make sure ophthalmic products are free foreign particles, as these substances will cause eye irritation. This directly affects the bioavailability of the product. This requirement is strictly applied to ophthalmic products in the form of solutions such as eye drops or lotions. For suspension type of ophthalmic products, this rule does not apply. However, we have to ensure that 90% of insoluble particles must not exceed 5 microns and no particle has maximum dimension more than 50 microns. To get a clear solution, we can use filtration using different types of membranes of various pore sizes. For example, microporous plastic membrane, sintered glass filter, and Whatman paper filter. Sintered glass filter grade 3 is commonly used in our dispensing laboratory. We move on to the second factor, tonicity. Isotonicity adjustment is important for ophthalmic products, as paratonic or not isotonic solutions are irritating to the eyes and can cause discomfort or pain. This would greatly reduce patient acceptance of the products. However, the argument against paratonic solutions for ophthalmic products is less supportive because evidence shows that the sensitivity of eyes to variations in osmotic pressure is much lower than that to pH and the nature of medicaments and preservatives. Generally, our eyes can tolerate paratonic solutions like 0.5 to 2% sodium chloride solution. However, it is best to formulate ophthalmic products isotonic to avoid unnecessary hazards. This can be achieved by adding salts like sodium chloride, mannitol, dextrose and so on. In order to know how much we need to adjust, you will need to refresh back the tonicity calculation as taught in dosage form 1. I would not go into details for the calculation, but you are expected to learn it on your own. Another important aspect in formulating ophthalmic products is preservation. It is very vital, as the addition of preservative can help to prevent the growth of and destroy microorganisms such as Pseudomonas aeruginosa. This then could maintain the sterility of products. Being an ideal preservative, it must be able to solubilize in the solvent used, being non-toxic, non-irritant and non-volatile. At the same time, it must have a wide antibacterial and antifungal range. As usual, being part of the excipients, it must be stable and compatible with drugs, other excipients, packaging, sterilization etc. There are several types of ophthalmic preservatives, including detergent preservative, oxidizing preservative and ionic buffered preservative. Detergent preservative reacts by interrupting the lipid component of cell membranes, and bacterial cell content will be extruded from the cell due to membrane instability. This links to the bacterial cell death. Oxidizing preservative, on the other hand, alters the lipid membrane but in a different pattern. It penetrates the membrane and alters DNA, protein and lipid components of bacterial cells. This type of preservative is less toxic. Ionic buffered preservative is one of the latest preservative available in the market. It reacts similarly like oxidizing preservative but less cytotoxic to the ocular surface. Benzalkonium chloride is a very classic preservative. It is active in a pH ranging from 4 to 10 and has a broad antimicrobial range but not Pseudomonas aeruginosa. It is less effective if pH less than 5, for example, in the presence of boric acid. However, it is not a problem as concentration of preservative used is way too low. As I said before, it is a detergent preservative. It has surfactant properties, which means it has the ability to break cell-cell junctions in the corneal epithelium, causing eye drops easily to enter the anterior segment of the eyeballs. One has to remember that repeated exposure or cumulative use of benzalkonium chloride can cause damage to the corneal endothelium. It can disrupt lipid component of the tear film and reduce tear breakup time. This leads to the tear film instability. It is a great problem for glaucoma patients. You have to be careful with the use of benzalkonium chloride as it has incompatibility with anionic compound, nitrates, salicylates, citrates, iodides, silver salts and a high concentration of non-ionic compounds. It is also incompatible with some packaging materials such as teats of the dropper with stearate and microcrystalline polyethylene lubricant. It is advised to change to silicone rubber teat with the use of benzalkonium chloride. However, since it is used at a very low concentration, this problem is negligible. Benzalkonium chloride is also known to become concentrated in contact lenses, especially those have been stored in conventional lens solutions. When placed in an aqueous ocular environment, the contaminated contact lens can act as a reservoir of preservative that can later be released and cause toxic to the eyes. Phenylmercuric nitrate, PMN or acetate, PMA is another example of detergent preservatives. It is active at pH 5 to 8 and has a broad antimicrobial range which covers bacteria and fungi including Pseudomonas aeruginosa. But the bactericidal action is slow. Unlike benzalkonium chloride, it is more stable at acidic pH except for PMA. The use of PMA may lead to hypersensitivity problem. It is known to react with halides to cause precipitation. Again, this could be uncommon because of very low concentration of preservative involved. Anyway, it is best to avoid the use of this combination. Apart from this, it is strongly uptake by rubber teats of the dropper for eye drops bottles. The use of organic mercurials can lead to mercurialantis, especially on long-term use or chronic use. Mercurialant is a brown discoloration of the anterior capsule of the lens caused by mercury, and this could be an early sign of mercurial poisoning. It is, thus, not suit for long-period use. The next category of detergent preservative is called biguanides. Chlorhexidine acetate is a common example. It is effective at neutral or slightly alkaline pH. For microbial coverage, it is effective to gram-positive bacteria but not spores, as well as low activity against Pseudomonas aeruginosa. It is not compatible with anionic compounds, several types of compounds or salts, as well as organic matter like serum and phospholipids. Here is the list of other commonly used ophthalmic preservatives like schlorocresol, chlorobutanol, paraben, thiamosyl and iditate disodium or EDTA. ED2 is also used as a stabilizer and has a synergistic effect with chlorhexidine acetate. Polyquaternium-1 or polyquad is a newer type of detergent preservative that is derived from benzalkonium chloride, where it does not become concentrated in contact lenses. Polyquad was formulated in the mid-1980s by Alcon as a preservative for contact lens storage solutions. It was developed because other preservatives were known to become concentrated in contact lenses that had been stored in conventional lens solutions. Bacterial cells attract polyquad, yet human corneal epithelial cells tend to repel the compound. Thus it is less toxic to the corneoconjunctival surface. The only downside of it is that it could decrease aqueous tear film production. Formulation scientists realized the need to get a newer type of ophthalmic preservative, as detergent preservative has so much disadvantages and problems. Oxidizing preservatives such as stabilized oxychloride complex is developed. Chemically, SOC is a mixture of chlorine dioxide, chlorite and chlorate. It was introduced into ophthalmic medicines in the mid-1990s under the trade name Purite. The antimicrobial effects are broad and include antibacterial, antifungal and antiviral effects. Stabilized oxychloride complex has been shown to be well tolerated by the ocular surface. Even at very low concentrations of 0.005%, the antimicrobial activity is broad. It has been shown to lack cytotoxicity in vivo. When exposed to light, it dissociates into water, oxygen, sodium and chlorine-free radicals. The chlorine-free radicals are thought to inhibit microorganism protein synthesis within cells, which causes microbe cell death. Lately, Sofzia, a type of ionic buffered preservatives, is the most recent advancement in the field of ophthalmic preservatives and is the preservative system contained in one preparation of travoprost for glaucoma. It comprises boric acid, zinc, sorbitol and propylene glycol. When exposed to cations, such as those that are normally encountered in the tear film of the eye, SOFZIA is deemed inactive. This is thought to induce less cytotoxicity to the ocular surface compared with more conventional preservatives. The SOFZIA system effectively preserves the medicine while it is being stored. However, when the drug is introduced into the eye, it is modified into harmless elements that are gentle on the ocular surface. It has been demonstrated that SOFZIA preserved travoprost induces corneal and conjunctival changes similar to preservative-free artificial tears. Furthermore, travoprost with SOFZIA also induced reduced amounts of conjunctival inflammation and corneal changes when compared with travoprost treated with benzalkonium chloride. Early on in the first lecture, we mentioned about the weak buffering capacity of our tears being a great disadvantage as it cannot tolerate strong acid or base. This is why pH and buffering become a real concern in formulating ophthalmic product. Despite the weak buffering capacity, it is enough to quickly neutralize pH of unbuffered solution from pH 3.5 to 10.5 provided it is a small volume of 1 to 2 drops or 0.05 to 0.1 milliliters. The buffering capacity of our tears actually comes from the source of our tears, which is carbonic acid, proteins and weak organic acids. Most ophthalmic drugs are salts formed from strong acid or weak organic base such as atropine sulfate, pilocarpine hydrochloride and physostigmine sulfate. Therefore these drugs are most stable at pH 3 to 5. A pH or buffer selected for an ophthalmic product must achieve the optimal stability of the drugs so it won't compromise the efficacy. At the same time, it can help to solubilize the drugs at a certain pH range selected. Buffering capacity of the buffer used must be sufficient to resist the adjustment by tear fluid so it won't affect drug stability and solubility. However, this may cause discomfort to the eyes. In another circumstance, if the ophthalmic product is neutralized rapidly by tears, it does not cause discomfort but it may jeopardize the stability of the drug. It is therefore very important to select a right pH range or buffer for ophthalmic products. Now, you should know the function of a buffer in ophthalmic products. It helps in improving drug solubility and bioavailability, the efficacy of preservative and stability of product while reducing irritation. A good buffer must have a narrow buffering capacity around ocular pH so it won't cause much irritation to the eyes. It must be chemically stable and has a minimum or no interaction with drug excipients. Also, it must be isotonic or has no effect on tonicity. There are several types of buffers which you can use for ophthalmic products such as borate buffer, phosphate buffer and citrate buffer, depending on the pH range desired. All of them are isotonic and consist of a combination of different salts or compounds. Borate buffer contains boric acid which is incompatible with divalent metals or above and forms insoluble borates such as aluminium, iron, ferric and zinc. It may also react with glycerin to form glyceroboric acid. Alkaloid, which is a class of nitrogenous organic compounds of plant origin that have pronounced physiological actions on humans, may not suitable to use with borate buffer. Even though alkaloid is soluble in water, its bases are not soluble in water and cause precipitation with borate buffer. However, it may not always true as the bases are usually slightly soluble in water. There may be an unbuffered system for ophthalmic products. For example, ofloxacin in ophthalmic solution as it is formulated with a pH of 6.4. As we know now the basic composition of an ophthalmic product, we need to know the typical vehicles used for these products. There are generally two types, aqueous or oily vehicles or formulation. For aqueous formulation, sterile distilled water or purified water USP are usually used, or the water can be sterilized together as a final product. The water-based system would definitely need a preservative. However, for oily formulation such as ointment, the vehicles used are typically vegetable oil, mineral oil and petrolatum base of high purity. It is important to make sure they do not degrade easily. The following 2 slides will show you a list of commonly used isotonic vehicles in USP which may be buffered. You may use the ready formula for formulating your ophthalmic product. We have here isotonic sodium chloride solution which is not buffered. Addition of buffer may be needed. Boric acid vehicle and special boric acid vehicle are buffered isotonic vehicles. Over here, we have isotonic phosphate vehicles or Sorensen's phosphate vehicle and borate buffer which provide a wide range of pH which you can choose based on your drug. With that, you have a basic knowledge of the vehicles and some essential ingredients on the design of an ophthalmic product, namely aqueous formulation. Thank you for your attention. See you in the next lecture for the part 2 of the formulation consideration and assessment of ophthalmic product.